Ever wonder why some AI detection tools outperform others? Or how researchers turn raw models into precision instruments? Let's explore a revolutionary approach. Evolutionary algorithms, a computational mirror of natural selection that lets machines learn faster, adapt smarter, and solve problems no single model could crack alone. Imagine you're designing an AI system from scratch. You start with a chaotic mix of parameters, test them, and keep the ones that work. Then you combine their traits like genetic material, introducing tiny random changes to spark innovation. Repeat this over generations, and you end up with a model that's not just functional, it's optimized. This is evolutionary algorithms in action, a process that's reshaping AI development. Here's the technical breakdown. 1. Initialization. Researchers generate a population of random model configurations. Think of these as diverse, genetic codes for AI, each with unique parameter setups. 2. Evaluation. Each model is scored based on performance metrics, like accuracy in detecting AI-generated text or efficiency in processing data. This fitness score determines survival. 3. Selection. The top-performing models are chosen to reproduce, passing their parameters to the next generation. This mimics survival of the fittest. 4. Crossover and mutation. New models are created by combining traits from the best performers, like genetic recombination, and introducing controlled randomness, mutations, to explore novel solutions. 5. Iteration. This cycle repeats, with each generation refining the model's capabilities until it reaches peak performance. Why does this matter? Evolutionary algorithms aren't brute force guesswork. They emulate nature's problem-solving strategy. For instance, in a recent study, researchers used this method to enhance AI detection systems. By testing thousands of parameter combinations, they identified subtle patterns, like typing rhythms or linguistic anomalies, that outperformed human experts. This approach isn't just about speed, it's about adaptability in dynamic environments. Let's get technical. In one experiment, models evolved over 100 generations. Early iterations struggled with false positives, but by generation 70, accuracy surged to 93%. This highlights their ability to adapt to complex shifting tasks, like distinguishing between human and AI-generated text, even when input styles evolve. It's a digital arms race, where each generation outpaces the last through iterative refinement. The takeaway: evolutionary algorithms aren't just a tool, they're a paradigm shift. They power everything from fraud detection systems to drug discovery pipelines, enabling machines to self-optimize without explicit instructions. Imagine an AI that evolves to handle new data distributions, or a voice assistant that fine-tunes its responses in real time. This is the future of adaptive intelligence. Next time you interact with AI, remember, behind the scenes it might be evolving to improve. Thanks for watching. If you want to see these algorithms in action, subscribe for deeper dives into AI's hidden mechanics. And drop a comment. What's one challenge you'd love to see evolved with this technique? Let's keep the conversation going. But how do these algorithms find the perfect configurations? Let's zoom in on hyperparameters, the invisible dials controlling a model's learning process. Think of them as the throttle, brakes, and gear shifts of an AI car. Should it learn quickly or slowly? Should it prioritize simplicity or complexity? These choices define its performance. Traditionally, engineers manually tune these settings, but that's like adjusting a car's engine while it's moving. Instead, machines now run thousands of experiments, testing every possible combination. They act as both mechanic and driver, refining parameters like a sculptor chiseling away imperfections. Over time, they retain the settings that yield the best results, creating models that improve autonomously.